Welcome to my lecture on slope stability. Slope stability, it is a numerical analysis. Nowadays we are seeing landslides. So in the numerical way, how it fails. So that is what this unit going to be discussed. So we can split this slope stability into two major topics. One is infinite slope and another one is finite slope. Infinite slopes are the slopes which are nothing but natural slopes. Finite slopes are nothing but man-made slope. So what are natural slope? What are man-made slope? In a sense, so the natural slopes are nothing but mountain slope which are extending for several distance from top to bottom. It has in terms of meters, it leads to 500 meters, 600 meters, likewise. So it also has length in the, by the way, it's going up to several kilometers. For example, Western Ghats has several kilometers starting from Kanyakumari to Gujarat. It goes too long. So it is categorized under natural slopes. So those are as well as known as infinite slopes. Whereas finite slopes has some finite definite dimensions. So that is possibly man-made slopes. So we have a slope like this. Whereas the slope is made to impound water in case of earthen embankment, which is running for several meters. Okay, whatever may be. So this is it has final dimensions as constructed by man. So that is what it is an man-made slopes. So it is an earthen embankment slopes, or in case it may be purpose, it serves the purpose for some any highway embankments. So whatever may be. So that is coming under finite slope. So in this topic, so the slope stability. So in infinite slope, by the way, in this mountain, we may need to cut this mountain to give some any transportation to reach the top level. So maybe it may be UT or Kodaikanal, whatever it may be. So the road has to be constructed. So in order to construct this, we are going to start the site investigation. That site investigation is nothing but slope stability. We are going to cut like this and we are going to apply some load. So this slope has to be withstand for this load is to be given. So in order to give a proper road, so the slope must be very stable, so it can able to stand for landslides. So landslide may occur, so the slope has the feasibility to landslide, it is susceptible to landslide or not. So that slope stability, that is what we are going to see in infinite slope analysis. In finite slope analysis, so this is the case. In finite slope analysis, so this is a very flatter slope. So this is what very flatter slope, and this is very steeper slope. So this height and this height both are same. Say consider h. So comparing to this is a flatter slope which consumes too much volume of soil, whereas this steep slope may consist very less volume of soil comparing to this. So this is a cross sectional area A1. So this is cross sectional area 2, but height is same. So this A1 is going to be higher than A2. So whereas this is running for several distances, so the volume need to be borrowed from any earth pit. So this is an borrow pit going to be digged and collected sample has to be transported and it has to be compacted and it has to be filled to form this dimensional finite slope. So whereas when you are making this slope steeper, so the area is getting reduced as shown here. So whereas the area reduces, for the several meter length, the volume of soil need to be excavated and transported is going to be less. So the steeper the slope we are going for towards the economical point of view. So that is what we are going to discuss in the finite slope analysis. So what is an possible steeper slope? So that can stand to serve our purpose is nothing but finite slope analysis. Infinite slope analysis serves for this purpose. So let us start with the infinite slope analysis. So what is infinite slope analysis? It is nothing but, so all the in case of whether it is an infinite slope analysis or finite slope analysis, it is deals with factor of safety. Let us say factor of safety equals to 1. So I will be discussing this. Factor of safety equals to 1, that is an critical slope. It is about to fail. When factor of safety is lesser than 1, it is an unstable slope. Factor of safety is greater than 1, it will be stable slope. So how to get this numerical value? It is less than 1, equal to 1 or greater than 1. How much it is? So greater. So that numerical value I am going to derive it for you. So here infinite slope analysis, or it is nothing but translational failure. So this is an mountain slope. So by the way, digging towards the center of the earth, we are going to reach, say this is an layer 1 and this is what layer 2. So when so this is an layer 1 and this is layer 2, we have an some plane forming here, layer 1 and layer 2 it have some form layer. So this slope may get fail. So that is what we call it as landslide. When this will fail, in case factor of safety is greater than 1, so this slope doesn't fail. How much it is safer, say in case of 1.5 times, so it has a ability to stand for 1.5 times against the landslide. So that is what a translational failure. So this is what a translational failure, moving in a linear direction, represents translation failure. In case at the end of the some derivations I am going to discuss. So if I found factor of safety is greater than 1, say it is 1.5 times, 1.5 times it is safer. So that is the numerical meaning of this. So this is what a landslide. So in order to start this, you need to be understand Coulomb's equation, so which I have already explained in my earlier video. Coulomb's failure envelope for phi soil. So this infinite slope stability, let me first discuss the phi soil in this case here. So Coulomb's failure envelope, this is sigma n and tau. So this is failure envelope. So here it is critical slope. Say this is phi. In case this slope angle is I, slope inclination angle I. So when this is an angle of internal friction or angle of repose, we say when this phi equals to I, so it is in critical slope, this slope is about to fail. When my I is greater than phi, this is not a possible slope, it is unstable slope. When my I is less than phi, so this is perfectly stable slope. So factor of safety is greater than 1. So this is unstable slope, factor of safety lesser than 1, it is not a possible slope. So I can explain you here. If you are taking a handful of soil and pouring over this table, so it forms some angle with respect to horizontal. So that is what this I am coming to say. So once you pouring handful of soil, cohesionless soil, so our discussion is cohesionless soil. So you poured handful of soil over this table, so it forms some angle with respect to horizontal, that is nothing but phi, as I told. So this is the value of phi. When you are trying to hopper it to very steeper level, you cannot make it. So this is not possible slope, unstable slope. So the slope inclination angle greater than phi is not possible, you cannot make it. So that is what I told, it is an unstable slope, it is not a possible slope. But when you are taking it, it is going down, you can make this phi slope can be flatter than this. When you are making it flatter, when I is lesser than phi, so this is perfectly stable, there will not be anything. So if you are hopping it steeper, once you are hopping it steeper, the particles will be start sliding down. So this is not possible, but you can, if you are make it flat, trying to make it flat, so that will become stable slope. Whereas this f is greater than 1, so this is f is equals to 1, so this is unstable slope, f must be less than 1. So this is a small example I can give you with explanation to this. Now I can give you another simple example. So this is through which you can clearly understand what I am coming to say. So let us consider a rotating pad like this, tilting pad. So it is hinged, so this is a pad, let us say this is a pad, so this can be moving like this, so it can move, it can able to move, so it is hinged here. So from horizontal to vertical you can tilt it. So let me place a object like this. So let me place an object like this. So what happens? So let us consider this is an CG. So this self height of this object is going to be exactly directly below, say W. When I am slowing, so this is let us say at horizontal level, let I am slowly increasing it, and at one inclination angle you are slowly increasing, so 0 to some angle. When slowly increasing at some angle, it is going to be slide down. It is going to be slide down. So that is an example I can to match here. What happens? So let me, so once I am slowly increasing the angle of this pad, so there is an frictional force will be developing. So this is the thing you must need to be understand. So this is the frictional force which is developing. So that is the frictional resistance doesn't allow this mass to slide over along the plane. So what is the value of frictional force? So this material, whether this plane has some frictional coefficient, the frictional force given by F equals to frictional coefficient into normal force. So by the way, this is a normal force. So this is acting force and this is acting normal force. So this line is frictional force. So when I am slowly raising this, so frictional force will be holding this mass not to slide down. Once it is reaching particular angle, this starts sliding down, which means the frictional force developed is not equal to hold this. So I can give you very simply what I am coming to say. So this weight is a main playing background. So this weight is nothing but gravity influence. So whereas this slope also is going to, because of the gravity influence only. So this is an gravity influence W. When the slope is, so this is an driving force. So this is going to be a driving force. The mass is coming down. So this is going to be the normal force. This W is going to contribute to both driving force as well as normal force. So this W, let us say when slope is coming steeper than this, so this W is going to contribute more to driving force comparing to N, because this is W. So this W remain as vertical, but this angle, FD angle, this angle is coming down. So let us say this is 30 degree, presently it is coming down to 10 degree. So when this angle reduces, this weight is going to contribute more to driving force than your normal force. But what is coming here? So the frictional force developed is entirely dependent on normal force. When normal force N1, let us say N1, so N1 is higher whereas N2 is lesser. So N2, when the slope increases, so the normal force acting on this plane is slowly start going down. So this normal force is start going down, the frictional force also going down. So the frictional resistance which is developed in the opposite direction, when goes down, it starts moving. So that is what translational failure, as I have explained here. So there is a very basic example. So the slope increases, the weight will be contributing much to the driving force that is going to slide your soil along any plane. So when this slope is flatter, it is safe case because this normal force hold the sliding mass doesn't fail. So that strength it has offered, so that doesn't, it is failed. When the slope increases too much, so the force developed is not capable to against this driving force. So that is a major concept. So with the help of this I am going into the some derivational part. Let me first explain the cohesionless soil, a slope which consists of cohesionless soil or phi soil we can say. By the way, this is an slope. Let us consider this is an layer 1 and layer 2. By the way, along the slope, so it has some layers. So I am considering some small portion like this. Why I am taking like this? By the way, I am going to start the investigation on the slope. I am start digging from here. So I am going for in a vertical direction only. I cannot dig like this in this horizontal manner, in this inclined manner. So I am digging in a vertical manner to look for the any soil profile variation. So I have found the profile variation from layer 1 to layer 2 at this level. So let me take this as Z, so which I have got in field. By the way, it does I am measuring some that critical portion in this distance as well. So this is an distance measured with the help of a tape, we can say. So as tape measured, so this is an B distance. So this is starting from this is going to be a B section. So and this slope is going like this in infinite length. By the way, it is an infinite length. Let me consider this is for 1 meter. By the way, this is 1 meter. What I am coming to say, so let us say this is an center of gravity W. In order to analyze this stability of slope, as I told, we are going to do factor of safety. So the factor of safety, it is nothing but, so it is an frictional force developed, as I told in my previous example. This is now, it is not a frictional force, it is a shear strength of soil, that is what holding this soil not to fail. So this is an tau F. So this is an generate available shear strength tau, and what the sliding force is driving force going to fail the slope. So this is an available strength. So what is this sliding stress? So that is has to be put into denominator. By the way, we can get factor of safety. So this is going to be favor us and this is going to be against us. So the favor us is going to be at the numerator and denominator is going to be the sliding force. Let us say this is an driving force or sliding force. Let us say FD, it is an driving force. So this is available shear strength divided by, so this is an tangential stress, it is going to develop tangential stress, so T, or in terms of F equals to tau F is an available strength. So tangential stress is nothing but FD divided by contact area. So this is an force, so tangential stress, so this is also represented by tau. So force divided by this contact area is nothing but FD divided by A. So as you know, tau F is nothing but C plus sigma n tan phi. So whereas I have considered only cohesionless soil, C is going to be as 0, sigma n tan phi will be there and tau T will be there. So in order to find out the normal stress acting on this, so tau F which is developed is entirely dependent on normal stress which is acting exactly on this plane. So tau F sigma n acting on this plane, sigma n which is acting on this plane is going to be the reason for tau F. So how to find this sigma n? So the only solution we have is to find W. So W, so this is what normal force, this is in terms of stress value. So this, in order to find this n value, normal load acting on this plane, the only solution we have to find W. So W can be, with the help of W we can find driving force, also we can find n. So how to find this W? So this is weight of sliding mass. How to find this weight of sliding mass in the sense? So let me draw this same portion. I'm just zooming in. So this is what B and this is what is it. So let me draw a line like this. If I cut this triangle and I am placing it here, it is going to be exactly fixed in the place. So I am cutting this and placing here, it is going to be exactly fixed into the position. So and it becomes as Z value, and I doesn't know this value. So this is, let us take this slope is inclined in an angle of I. So this is going to be I value here. So we doesn't know this x. So this x is nothing but cos I. So this is an adjacent type. So it is an right angle triangle. So this is adjacent side. Cos I equals to adjacent side x divided by hypotenuse b. So x become as b cos I. So this is nothing but b cos I, and this is as z as it is, and this is will be 1 meter. So this is 1 meter, and this is b cos I, and this is up to z value. So this is w. So I am just shaping this into as this in order to compute weight. So weight is nothing but this is volume. So volume into unit weight of the soil, you are going to get weight. So how to compute this volume V? So it is an b cos I into z into 1 meter into multiplied with gamma. So we will be getting this gamma z b cos I is w value. So now we found out what is an w acting here. So this w will be, using this w we can find n and we can find fd with using simple engineering mechanics. So how to find this? Before which, so if I am drawing an horizontal line, so if this is I, this is also I. If I am drawing a vertical line, so this forms 90 degree. If that is 90 degree, this is I, this is going to be 90 minus I. So this is also going to be 90 minus I value. So what I am coming to say is, so this is along the slope, this is n and this is ft and this is w. So look at this. So this is what I have drawn here. So this is 90 degree. So this is 90 degree. So this is a vertical line. So this is vertical line. So this line going to be same parallel here. So this is 90 minus I. So this is also 90 minus I. So this is coming as 90 minus I. So if this is 90 degree, so this is going to be I. So this is 90 degree. So this is 90 minus I. This is 90 minus. When we have any force component, so it has to be converted to some included angle. So FD is nothing but W multiplied with cos 90 degree minus I. Simply we can use the help of cos included angle, you will be getting this force component. So N is given by, so the same W into times cos I. So by the way, simply we can compute, so FD equals to W times, so cos of 90 degree minus I can be written as sin I. So by the way, this is an weight component, I mean force component. In order to convert this into stresses, so in terms of stress, tangential stress is nothing but force divided by area, I told. So W, what is W? Gamma is at B cos I divided by area is nothing but, so this is what then a plane area subjecting to the stress. So that area is nothing but, so this is B, so this is B into 1, B into 1. So B get cancelled, gamma is at cos I is an, it is an FD value. So FD value so this is W, so this is W into, so this sin I, I am writing is here sin I, so this is coming as sin I. So tau T is taking into form of sigma z cos I sin I. In order to find this normal load, so I have written normal load W into Zi. So this is written as sigma n. So this, let me take this is as sigma Z. By the way, I found, so same contact area, so sigma n value is nothing but same n by a. So here also w into cos I, so the w is gamma z b cos I into cos I divided by b into 1, so b get cancelled, it is gamma z cos square I. So this is, so these things are very major, sigma n. So while coming to find out this factor of safety equals to 1, sorry, factor of safety equal to sigma n tan phi. So the sigma n value in terms of stress value, sigma n is gamma z cos square I is in sigma n into tan phi divided by tau t, it is gamma z cos I and sin I. So this is cos get cancelled, so tan phi divided by sin I divided by cos I. So this can be simply written as tan phi divided by tan I. So this is a thing, never forget this, very important. So F equals to tan phi divided by tan I. If I am substituting, let us say the soil tested in the laboratory and will give you the value of tan 45 degree. So tan 45 equals to 1. Let me take the slope inclination angle 60 degree. Tan 60 degree is greater than 1. Tan 60 degree is greater than 1. So 1 divided by greater than 1, it is going to be less than 1. So that less than 1 value, so the factor of safety coming lesser than 1, it made this slope as an unstable slope. By the way, we have some different cases. So this is for dry or partially saturated sample, soil sample. So we get factor of safety equals to tan phi divided by tan I. When phi equals to 45 degree, this is going to be 1 divided by tan I also 45 degree is going to be 1. So it is a critical slope. When phi equals to I, so there is going to be a critical slope, as I explained earlier. So we have some other cases. The slope actually we are thinking as a safer slope will not be safer. Say for example, in case it is in 45 degree angle of intersection, let us say tan 30 degree. So it may be giving you some value. By the way, it increases to 1.73. So by the way, we have got this factor of safety as 1.73. Let us say like this. So we have some different conditions. Submerged slope we see. What is submerged slope in the sense? So this is a slope. So when we are constructing a dam or whatever may be, so the water level is increased like this. So this is an present water table. So this stretch of slope is nothing but submerged slope. So and this slope is going to be dry slope. So in this case, whether your slope is stable or not, in order to compute that, when I am doing so everything, so what I am getting is F as I have done earlier. So gamma z cos square I into tan phi divided by gamma z cos I into sin I, which is an equation for the previous derivation. So by the way, so this is a submerged slope, this stretch is submerged slope, this is dry slope. So this submerged slope has an unit weight of gamma dash. Just replace gamma dash both the side. So this is getting cancelled. I am getting tan phi divided by tan I, the same. It doesn't change anything. But here instead of gamma dash, I have to put, instead of phi, I am going to put phi dash, because it has some effective pressure principle going to be work here. So that is why I have to put phi dash. So now I am having different cases. So let us say a steady seepage case. Steady seepage along the slope. steady seepage occurring along the slope in the sense, so this is the slope by the way. So during the rain, so it is so the water is get infiltrated and stored. Say this is maybe a rock, so water cannot penetrate through rock, so along this rock, so the water is going to run along this slope. By the way, it is full like this much of water is flowing along the slope here. So the F is given by, let us say, sigma n tan phi divided by tau tangential as a initial way here. So this is what sigma n acting. Actually this sigma n is reduced somehow because of this pore water pressure developed. So this is an water pressure, this is water pressure, how much water pressure can be developed. So the actual pressure which is acting over this in this normal to in this plane will be reduced somehow with this value, so that pressure is coming down to sigma n dash. So the sigma n value is going to offer some resistance against the sliding. That force eventually got reduced because of the pore water pressure which is developed. How much the pore water pressure is developed is nothing but sigma n dash equals to sigma n minus u. So this u can be computed and with the some same derivations which I have right here. So by the way, if suppose this portion is considered as water and this sigma n as computed here, by the way, we instead of this gamma you are going to put gamma w. So if you are calculating like this, this u is going to become gamma w is at cos square I is going to be the pore water pressure in this direction, which is opposing the normal stress direction. So here gamma z given and this z value is going to be zw. So what is the depth of pore water? So whereas we consider this z equals to zw, so which means this water is flowing at full level, let us say. So z is going to be zw. So now sigma n dash is going to be substituted as sigma n minus u. So factor of safety equals to sigma n is gamma sach z cos square I is an sigma n value minus u. I am going to substitute this gamma w same, but for this case I am keeping this z as the same, cos square I into tan phi divided by gamma sach. So this tau t gamma sach cos I and sin I. So this is going to be the same, gamma sach minus gamma w will become as in gamma sach z cos square I. So gamma sach minus gamma w will be gamma dash z cos square I as taken out as a common term into tan phi will be remaining. So gamma sach into z cos I and sin I will be remaining. So z is get cancelled. So turning into shape gamma dash divided by gamma sach into tan phi divided by tan I. So actually the slope which we are thinking as a safe in dry or partially saturated conditions. So here, so this tan phi divided by tan I for 45 degree, 30 degree, it is going to be the value of 1.73, which means this is 1.732 value, and further it is reduced to, so gamma dash, what is gamma dash value? It is gamma sach minus gamma w. Usually gamma sach is about 20 kilonewton and gamma w about 10 kilonewton per meter cube. 10 kilonewton per meter cube. So this is gamma sach value is going to be 10. So this is 10 divided by gamma sach is 20. So it is about 0.5. So this 0.5 into 1.73, it is going to be 0.867 like this. So it is lesser than value. So the slope which we are thinking greater than 1, it is stable slope when it is dry or partially saturated. When the rain comes, it changes everything. So when rain comes, the factor of safety is going to be lesser than 1, so during the rain season that slope doesn't stand, it fails definitely. So as we have seen in 3 different cases, so dry or partially saturated slope tan phi divided by tan I, so going to be the same value. Submerged slope nothing changes, tan phi divided by tan I, so okay it is, but the steady seepage slope it fails. So water may be in the slope if it faces any earthquake loads, so there it fails. So there are some other several cases, so this earth slope may take any vehicle load, there it may be changes. So for the different cases like this, so I have explained 3 cases here, so likewise case 4, case 5 can be explained. So we have to test factor of safety for all the cases. So which is the worst case factor of safety need to be taken into account. The thing which we have seen is nothing but factor of safety analysis on phi soil only. So whatever you have seen up to here is investigation on phi soil only, slope stability analysis. We are going to see phi soil analysis. So this is explained in terms of phi. So this is going to be factor of safety 1. So this is going to be factor of safety greater than 1, and this is going to be factor of safety less than 1 as analyzed for phi soil. So for phi soil the case is different. So this is sigma n and tau. So this is what an failure envelope. Failure envelope cases. So this forms phi value. Let us consider a slope like this. So in the previous case, when phi equals to I, in the previous case I equals to phi, it is about to fail. It is a critical slope as I have explained. So here this is an inclination, slope inclination. This is in failure envelope. So when I equals to phi, so this is going to be exactly parallel with this, and this is perfectly stable slope because it doesn't meet any failure slope here, failure envelope here. Whereas when I equals to phi, the failures, it is merging with failure envelope. So the inclination, slope inclination angle merging with failure envelope. So that is why I have told this is an failure about to fail. Whereas this stable slope inclination line doesn't meet failure envelope anywhere, so it won't fail. So this stable slope has factor of safety greater than 1, very stable slope. If I is less than phi, so that is also very much stable slope, f is greater than 1. So for both the cases I less than or equals to phi, so it never fails, so factor of safety is greater than 1. But when the slope is, when slope has I is greater than phi, by the way I is greater than phi, so it is going to meet the failure envelope at some point. So this is maybe that point. So this height is known as critical height. It is very major point to be denoted. So critical height, which means my slope can be greater than phi for cohesive soil. In case of cohesive is here, it helps the soil to go beyond phi value. So I can go beyond my phi value. So I am increasing this slope inclination beyond phi. So by the way I am going, so it meets this failure envelope at some point. So that respective height is taken as critical height. So our cohesiveness of soil helps us to form steeper slope than phi. So in this case you cannot form a slope greater than phi, is definitely not possible. Anyhow, cohesiveness of soil is helps to make slope greater than phi, but it works up to certain height only. That height is known as critical height. So how it works, let us see in some derivational way. So how it works. So by the way, same portion may be taken like this, and this tau which is developed is tau f. So this is tau tangential force going to be driving because of the driving force. So this tau f is going to be c sigma tan phi, because c also contributing here. So the factor of safety given by c plus sigma n tan phi divided by tau t. So this can be written c plus sigma is it cos square I stands for sigma n into tan phi divided by tau t is nothing but, sorry, this is gamma z cos I into sin I. Now we doesn't know the critical height yet, but this critical height refers that, so when it meets, it means the factor of safety equals to 1. When it crosses, say, let me take this height as a h, this is not a possible height to form. So what is this hc or h refers? Just nothing but this is what taken as hc. In the previous derivation I have taken it as z, that z is nothing but hc. When z greater than hc, it is definitely going to fail. When z equals to hc, it is an critical slope. When z is less than hc, it is going to be a stable slope. This is unstable. So this three cases exist, whereas slope inclination greater than phi. So when z equals to hc, the slope is going to be critical. By the way, we are substituting factor of safety as 1, that refers critical slope. So gamma z 1 equals to c divided by gamma z cos I sin I, plus z has to be replaced with critical height here. So which means, so it is hc up to depth is only possible. So if I am increasing this value greater than hc, so that slope going to be definitely failed. So if there is a slope lesser than hc, this h never fails. That is what it refers. So gamma z cos square I into tan phi divided by gamma z cos I into sin I. I can rewrite this. So this is a factor of safety 1. So this is all the cases when I is greater than phi only, it can be equals to 1. So by the way, it is coming to, in order to replace this, so 1 equals to this is a general case f is greater than I. So this is a, it is in factor of safety, that is in general format. By the way, it is in a general format, factor of 51 for the critical slope. So to get the critical slope, so I am substituting 1 here. So c plus gamma hc cos square I into tan phi divided by gamma hc cos I into sin I. I am taking this here, gamma hc cos I and sin I equals to c plus gamma hc cos square I into tan phi. So to get this hc value, finally it is ended up with c divided by gamma into 1 divided by tan I minus tan phi divided by cos square I. And I am rewriting this, I am getting this value, and it is finally turning this into c divided by gamma hc tan I minus tan phi into cos square I. So this can be replaced and written as Sn. So c divided by gamma hc equals to Sn. This is nothing but Taylor's stability number. So this is Sn value, Taylor's stability number. So this can be also rewritten into some other form. Sn equals to Cm divided by gamma h. So which means this is an mobilized cohesion. Factor of safety with respect to cohesion is available cohesion divided by mobilized cohesion. So factor of safety with respect to height is critical height divided by any possible height. By the way, for different cases to say submerged slope, so when Z is less than HC, F equals to C plus gamma dash Z cos square I tan phi divided by gamma dash Z cos I into sin I. So we can be rewritten this into HC equals to C divided by gamma dash into secant square I divided by tan I minus tan phi. So this is an critical slope when H is less than HC. Sorry, this is H equals to HC. So Z equals to less than HC. So factor of safety will be like this. So when H equals to Z equals to HC, so just replacing this Z values into HC, and it can be transformed to get this format. So this is a case 2. Let me write case 3, seepage along the slope. In seepage along the slope, Z is less than HC, so F is written as C divided by gamma sach cos I sin I plus gamma dash gamma sach into tan phi divided by tan I. Whereas Z equals to HC, which means factor of safety equals to 1, we finally getting this HC value into equals to C divided by gamma sach tan I minus gamma dash divided by gamma sach tan phi into cos square I. So these are the different formats for different cases. So when it is submerged slope, Z is possibly lesser than HC. So this is what factor of safety find out formula. When in order to find HC, this has to be make factor of safety equal to 1. So substituting 1, we are finally ended up with the HC formula as this format. And by the way, for seepage along the slope, we are getting possible equations so like this. So I hope you have understand this infinite slope analysis for phi soil and C5 soil. So phi soil, you cannot go the slope angle beyond phi, whereas your C5 soil cohesive helps to go beyond the phi angle, but it is limited up to the critical height called HC. So HC is a major thing. So this is limiting height. So I can be greater than phi, but up to limited for this HC height. So when H goes beyond HC, it is not a possible slope, it fails. At HC, the factor of safety equals to 1. So H is below HC, the factor of safety is greater than 1. So I hope you have understand my infinite slope analysis on phi soil and C5 soil. Thank you.